In this set of slides, we're going to walk through the first part of Chapter 4, which covers processor technology and architecture. And I think I'm going to cover about 20 slides from this slide set, which is maybe, I don't know, a third, 40% of the chapter, something like that. Concentrating mostly on the issue of instructions and instruction sets, the relationship between instruction sets and data representation, and then some related topics including simple versus complex instructions and CISC versus RISC processor design. One of the things I'm going to do as we walk through here is I'm going to bounce back and forth between the PowerPoint slides and between this particular Intel manual. This is the Intel 64 and IA32 Architecture Software Developer's Manual. There's actually 5 volumes to this manual. This is volume 1, just basic architecture. And this is by far the easiest to read, which does not say it's the easiest to read. Kind of gives you an overview of things like the execution environment, data types, instruction set, and basically what I'm going to try and do is illustrate various topics that we're talking about in the chapter with specifics from this Intel manual. This is, I believe, the 2009 version, June 2009. If you go on the Intel website, you can download this. By default, it may show you a later version, but that shouldn't be that much different from what we have here, and you can probably get the earlier version if you want. Okay, so let's get started here. First, just a quick overview of the CPU and its basic components and the functions of each of those components. So, as we discussed back in Chapter 2, the CPU is, for all practical purposes, the computer system's brain. Actually, I would add to that the role of traffic cop. So, the CPU is not only the smarts in the terms of processing, things like add, subtract, multiply, divide, but it's also the smarts in terms of determining where things come from and go to. So although some of the I/O functions are offloaded to other components within the computer system, the CPU can, whenever it wants, step in and control the flow of, say, data to and from memory, or from memory to the CPU and among registers, and so on and so forth. So in that role, it executes all program instructions. That includes computation and comparison and branching, as well as data movement, and it directs all computer system actions involving data movement, be they from primary storage, secondary storage, input-output devices, registers internal to the CPU, or so on. Okay, we can subdivide the CPU into 3 basic sets of components, and of course each of those can get broken up into much smaller pieces. The first component would be called the control unit, and it is essentially the part of the CPU that directs traffic, okay, and tells the other pieces what to do. So it's responsible for interacting with primary storage, for example, to read in instructions. It's responsible for breaking those instructions up into pieces, storing those pieces in various places, including registers. And it's also responsible for telling the arithmetic logic unit what to do. Actually, I see we lost a... there, let me save this piece there. Okay, the arithmetic logic unit, on the other hand, has a much more specialized job. Its job is to execute computation and comparison instructions. So you can think of the ALU as having a bunch of subcomponents, each of which is a set of circuitry dedicated to a specific computation or comparison function. So think of the ALU as being subdivided into other smaller units, say an add unit and a multiply unit and a divide unit, and so on and so forth. A less than unit, a greater than unit, and so on and so forth there. Okay. To enable or to provide both temporary storage spaces for the arithmetic logic unit to use as input or to store its output, and also to hold data in transit between the CPU and between other parts of the computer system, we have a set of registers. Okay, and basically these are single item storage locations within the CPU. They can hold inputs headed towards the arithmetic logic unit. They can hold the results of a, say, computation operation from the arithmetic logic, and they can hold other types of data. Their main purpose is fast access. Because they are implemented directly within the CPU, the circuitry of the control unit or of the ALU can access them very quickly and without delay. Whereas if the CPU has to go to, say, primary storage, or worse, secondary storage, or even worse, an I/O device, it will generally incur, or at least could incur, delays in that process. So by holding data that we're going to compute or compare or move around in the registers, we eliminate delays associated with accessing that data. Okay, this is figure 4.2, but it's actually a repeat from the second chapter, simply showing the CPU and the three components we've just described and their relationship to the other primary pieces of the computer system. Note that the CPU is connected directly to the system bus, which is in turn connected to primary storage or memory, secondary storage, and all of the devices that comprise it, and the various I/O units, things like keyboard and mouse and network card, that will enable the computer to talk to other computers or talk to humans. All right, so the CPU, so we've looked at the three primary components: control unit, arithmetic logic unit, and registers. But there's another way to think of the CPU, and that is to think of it as a device that constantly alternates between two states. Okay, and in the computer world we call those states cycles. Okay, and the two cycles are the instruction cycle, which is sometimes called the fetch cycle, and the execute cycle. Okay, the instruction cycle is where we bring in an instruction from main memory or primary storage and any data associated with that instruction. So for example, if the instruction is to add two numbers together, in the instruction cycle we read in the bit pattern that tells the CPU that, hey, we're going to do an add, and here's the two pieces of data we're going to do the add on. Okay, or that we're going to add together. Okay, so during that instruction cycle there is an access by the control unit to bring in the instruction from primary storage. Okay, there is an update of something called the instruction pointer, which is basically the address of the next instruction that we're going to access after we finish with this one. Okay, the instruction that's read in is at least temporarily stored in something called an instruction register. Think of that as just a scratch pad inside the CPU. If there is data embedded inside that instruction, then if, for example, the two items to be added, then they will be extracted from the instruction register and copied into other registers. On the other hand, in some processors, the add instruction, rather than having the actual numbers to be added with it, may have memory locations of where those numbers are stored, in which case the control unit at this point would go out to primary memory, grab those additional pieces of data, and store those in registers in preparation for having the ALU do that add instruction. Okay, so sometimes the data is part of the instruction, sometimes the data is actually just a reference, or I should say the instruction just includes a reference, typically a memory address, to where the data is stored, in which case the CPU has to go out, or the control unit has to go out and do some more fetching in order to get that data. Okay, once the instruction is in the instruction register, any data necessary to inputs for that instruction have been gathered and the instruction pointer has been updated. At that point, now it's time to actually do whatever that instruction says we're going to do. Okay, if it's a computation or a comparison instruction, then that's going to be the job of the ALU. If the instruction, on the other hand, is simply to move data around from one place to another, well, then the control unit itself does that. So in some sense we actually have two kinds of instructions: those which are executed by the arithmetic logic unit, which would typically be comparison and computation, and then data movement instructions, which are executed by the control unit itself. we can kind of look at this visually in terms of this diagram here, which is 4-3. This is the central processing unit here in the center. There's primary storage locations shown here on the left, and basically we've taken each piece of the instruction or fetch cycle and the execute cycle and shown them independently. So the first part, the first part of the instruction cycle is to look in the instruction pointer, say where in primary storage am I supposed to get the next instruction, read it in from primary storage. Then we're going to increment the pointer, instruction pointer, so that once we've gone through one cycle here, we're going to grab the next item. Okay, so this always points to the next instruction we're going to gather. Then we're going to take that instruction, we're going to store it temporarily in the instruction register, and if there are pieces of data associated with it as inputs, we're going to store those in separate registers. At that point, assuming it's a compare or computation operation, we hand off control, so to speak, from the control unit to the ALU. The ALU retrieves the instruction and the data. Okay, it does whatever is necessary to implement that instruction. For example, pass data 1 and data 2 through the appropriate circuitry to implement an add or whatever the function is. That generates a bit pattern that's a result, and that gets stored, typically in another register. At that point, the ALU is done. We transfer control back to the control unit, which immediately fetches the next instruction from the pointer. And so by constantly alternating between these two cycles, we step sequentially through a set of instructions, gathering data, storing them, pulling them out, feeding them to the ALU, letting the ALU do its job and store results. Now, on the website, there is an animation. Animation is probably too strong a word. What there is a PDF file, which is multiple pages. And on those multiple pages, what I did is I took this diagram as a base, and I took the simple programming example that's contained in Chapter 4, stored the instructions and data associated with that in primary storage, and basically walked through each step of the process to execute the instructions in that simple program. It's about 100 pages long, and basically the animation part is you just keep clicking next page, next page, next page, and it'll highlight which part of the control fetch cycle or the execute cycle is in process and exactly what registers are being read or written at that particular time. So that's a pretty good way to visualize what's happening in the programming example in chapter 4, and watching that operate, stepping through the pages, will give you a pretty good idea of the interplay between the control unit and the arithmetic logic unit, or between the instruction/fetch cycle and the execute cycle. So I'm not going to talk any more about fetch and execute here. If you want to look at that animation, go ahead and look at it, and I think you'll have a better idea of what's going on after you look at that. Okay, so let's talk about instructions themselves. Okay, so an instruction is basically just a set of bits sitting out there in primary storage somewhere. In more general terms, it's a command to the CPU, okay, to do one very specific processing function on one very specific set of data inputs. Okay, typically the processing functions are very simple. Add two numbers, subtract two numbers, move a data item from register 1 to register 2, that sort of thing. And the specific set of data inputs is relatively small. Typically there's either 1 or 2, or actually in a few cases no data inputs to the instruction. So we're talking about doing one very primitive or simple processing function on 0, 1, or 2 data inputs. Okay, and there's a pattern of bits that say what is the processing function, and additional patterns of bits that say what are the data inputs. Put those bit patterns together and you have a larger set of bits that constitutes the entire structure or instruction. Okay, when we read that instruction in from memory, or if it's already sitting in a register, okay, what we have is a sequence of bits, and basically what the CPU needs to do before it can do much of anything else is something called decoding. Okay, and the process of decoding is basically simply the process of looking at the instruction and breaking it up into its constituent pieces, which are the bit pattern that describes the processing function and the bit pattern or patterns that describe the data inputs. Okay, we of course have a special name for those. The bit pattern that describes the processing function is called the opcode, op short for operation. Okay, and a bit pattern that describes a data input is called an operand, and since it's possible to have more than one of those, we generally refer to operands in the plural. Okay, so the opcode is simply some part of the instruction's bits. Okay, and taking that bit pattern, say it's the first 8 bits, that forms a unique binary number that represents one specific processing function. Okay. The operands are sets of bits or groups of bits that follow the opcode, each of which contain data that's going to be processed by that opcode. And that could be the actual data itself, or it could be the location of that data, typically in a register or in a memory address. Okay, so the opcode is what we're going to do. The operands are what we're going to do it to, and the contents of the operands could either be the actual data that we're going to manipulate, or could be the location of that data, in which case the control unit's got to go out and access those locations and grab the data. Okay, so visually, here's an example down here at the bottom. I've got 8 bits dedicated to the opcode, and then for this particular instruction, I have 2 operands, one of which is only 4 bits, and the other of which is 8 bits. Okay, so for example, this might be an instruction that, say, adds operand 2 to whatever is stored in a particular register, and we'll assume that operand 2 is 8 bits or a byte that contains an actual value. Operand 1 is 4 bits that identifies one of 16 possible general purpose registers. Okay. Now, of course, different types of instructions might have different types of operators or operands. We might have an opcode, we might have a particular instruction with an opcode and 2 operands, but where both the operands are a byte long, or where both the operands are memory addresses, in which case they'd be 16 or 32 or 64 bits long, or where one is a memory address and one is a register number, or vice versa. Okay. So it's possible to have a lot of quote-unquote variations on what is essentially the same instruction with different types of operands, data, register numbers, memory locations, and different sizes of memory addresses or memory locations. Okay, so you get a lot of variation in instruction format depending on how many operands there are and what their type are. Okay, and the same quote-unquote processing function, such as add, might actually correspond to a bunch of different instructions, each of which has different patterns or different types of operands stored after it. Okay, so let's talk about some of the particular types of instructions we might find. Okay, one of the most basic ones we need is what we generically called a move instruction. Okay. And a move, for reasons I'll come back to shortly, is actually a copy, okay, operation. And what we're doing is we're copying data, actually just bit pattern, from one source to a destination. Typical possibilities here would be copying data from memory, from some particular address in memory, to a register. Okay, and we generally call that kind of move a load, okay, as in load the contents of the register from a memory address. Okay, we can of course go the other direction. We could take data that's already sitting in a register and copy it into primary storage to a particular memory address. We call that a store. So load and store are essentially opposites of each other. And of course we can copy data from one register to another. Okay, so there are various types of move. Now I've only shown 3 here, but in reality there can be a whole bunch more. And to illustrate that, let's come here to the Intel manual and let's look up data transfer instructions, which is here in section 5.1.1. Okay, here is an overview of all, they call them data transfer instructions, which move instructions. Note there is an actual instruction called MOV move. Okay, its job is to move data between general purpose registers, or between memory and general purpose registers. There's also something called a segment register, which I won't get into here. Okay, but note there's a whole bunch of other moves here. Okay, look at the second one. Conditional move if equal, or conditional move if 0. Conditional move if not equal. Conditional move if not 0. Okay, so on and so forth. Conditional move if carry. Conditional move if not carry. Conditional move if not overflow. Conditional move if sign negative. So on and so forth. Okay, these are actually examples of what are called complex instructions, and we'll come back to that several slides down the road. But this is a perfect example of what is conceptually a single processing function, but you've got a whole bunch of instructions that correspond to that, depending on what other stuff might be going on and what types of things might be moved to or from. Okay, so looking down this list, you see we probably got, I don't know, 30 or, whoops, jumped ahead too far. Probably got 30 or 40 different move instructions in a typical modern Intel processor. Okay. Now let's look at the second class of instructions, what I call the Boolean logic instructions. Okay, and Boolean logic instructions implement Boolean logic operations, which were covered back in Chapter 3. And you will recall briefly, we went over 4 of them. There's not, which basically negates or flips bits. So true becomes false, false becomes true, 1 bits become 0 bits, and 0 bits become 1 bits. There's the AND operation, which says if we have 1 and 1 yields 1, but any other possible combination is 0. Okay, and if we interpret 1 as true, that basically what that means is if I have a compound condition, both halves of the compound need to be true in order for the compound to be true. We have the OR condition, which says, okay, if both are false, then the result is false, but any other combination is true, or any other combination of 1s yields 1. And then we have something called the exclusive OR, which says if we've got 2 bit values or two data values 0 and 1, then the result is 1, but any other combination yields 0. So 0 and 1 yields 1, 1 and 0 yields 1, 0 and 0 yields 0, and 1 and 1 yields also 0. Okay, so in other words, exclusive OR says it's got to be one or the other, but not both. Okay. Okay, not both or not neither. Okay, so these are the logical operations. Now, one thing to keep in mind with the logical operations is that there's 2 ways to think of these. Okay, one is to think of them as operating on the values true or false. Okay, which basically means think of them operating on an entire bit pattern where the entire bit pattern, be it a byte or 4 bytes or 8 bytes, is interpreted as true or false. Okay, so not true becomes false, true and true becomes true, but we're thinking of it on entire bit strings. Okay, but there's another way to look at these Boolean logic operators, and that's what's called bitwise operations, and that's where you take each individual bit in a bit string and apply the not or the and or the or the exclusive or to it individually. So for example, if I have two bit strings that are 8 bits long each, and I say the first one not the second one, what I'm doing is not a not of one value to another, I'm doing a not of the first bit in the first operand to the first bit in the second operand, and a not of the second bit in the first operand to the second bit in the second operand, and so on and so forth. So if the 2 bit strings are 8 bits long, I'm in essence doing 8 knots at once, each on 1 bit position within the string. Okay, we'll come back and look at this a bit when we do an example, but just keep in mind for now when we're talking about Boolean logic, okay, there's 2 ways to think of it. One is per bit, and the other is per bit string, or per larger group of bits. Okay, so coming back and looking at the equivalent instructions in the Intel manual, these would be in section 5.1.4, the logical instructions. Okay, and we'll note we have AND, OR, XOR, and NOT. Note that by default they're all bitwise. Okay, there are additional instructions not covered here which handle these things in logical fashion. Okay, but these are by default considered bitwise instructions. Okay, so that's move and the Boolean logic operations. Let's talk about some of the additional instructions we could have. Well, we know that add is a very important one. Okay, and basically add does pretty much what you would think it would do. It would take two data values represented as bit strings and generate their arithmetic sum. Okay, so if we go and look at, say, binary arithmetic instructions, there's an integer add. Okay. Note also there's something called integer add with carry. Remember we have the possibility that an add produces an overflow, and this particular add instruction is designed to deal with that overflow, whereas this one above it is designed not to. Okay, but in addition to having an add for integers, we have adds for other types of data values. So we can't just have one add instruction. Okay, we need add instructions for integers, we need add instructions for floating points, and of course remembering from chapter 3, if we're following the IEEE 754 standard, there are actually three different kinds of floating points. There's 32-bit floating points and 64-bit floating points and 80-bit floating points. Okay, we need a separate add to account for each of those data types. Why? Because stepping back here, those data types would be stored in operands, and depending on which of those types we're using, those operands are going to be of different lengths. Okay. Also, the logic of the circuitry to do the add is going to be different depending on whether we're talking about integer data or real data, because integers are represented in 2's complement format, whereas floating point data is represented as a combination of sine and exponent and mantissa, and clearly the methodology or the circuitry by which we manipulate those two different data types is going to be very different. Okay, so the add instruction is really multiple add instructions, okay, because we've got different data types and formats, okay, and we need to look at short integers and long integers and unsigned integers and signed integers and 32-bit floating points and 64-bit floating points and 80-bit floating points, and of course if there's other types of data, ways of storing numeric data inside this processor, we're going to need add instructions for those as well. So the ones you're looking at here are only on binary arithmetic, okay? As it says here, basic binary integer computations, which are assuming that the things we're adding are integers and thus stored in 2's complement format, okay? Once we get into, for example, floating point instructions, let me come down here. Let's see, floating point basic arithmetic. So here's an fadd for floating point add, okay, and we also have and we've got various other floating points. So we've got basically different sets of instructions for floating point and for integer, okay, data. Okay, another very useful instruction is something called shift. Okay, what shift does is it takes a bit pattern and it moves all the bits left or right, okay, by a certain, however many positions we tell it to, and it fills zeros in on the missing pieces. And did I include the figure here? No, I guess I didn't, but there's a figure in your book. Let me see if I can find it very quickly. It's figure 4-5 on page 113 that you should take a look at, which gives you an idea, which gives you a visual of how the shift works. Okay. Now, just as in the logic instructions we talked about bitwise and logic versions of these, there's also two kinds of shifts, or think of it as two different ways to use a shift. Okay. One way to use a shift is what's called a logical shift. Okay. So for example, if I have a bit pattern, let's see, I'm going to pull up a notepad here real quick. Let's see. And let's just give a 0, 0, 0, 0, 0, 0, 1. Okay. If I have this bit pattern, well, there's a 1 that's in the rightmost position. Okay. Now, if I were to shift everything here 1 to the right, I would lose this 1, and I would fill in from the left with a 0, and I'd wind up with that. Okay. Now, the logical shift is generally used when I want to figure out what's in one particular bit position. So for example, let's say I've got 0, 0, 0, 0, 1, 0, 0, 0, and let's say for some reason I want to know whether this particular bit right there is a 0 or a 1. Well, what I can do is I can take this value and I can shift it to the right 3 times. There's my first shift. There's my second shift. There's my third shift. Okay. And because oops, I'm sorry. One more. Okay. So there's the result of shifting this value 3 positions to the right. Okay. In essence, I wind up with these original bits and then 3 new zeros padded in from the left. Okay. Now, why would I want to do that? Well, one reason to do that is because this value is a binary 1, which, as I know from chapter 3, I interpret as a true. Okay, so I can use this value to test it as a condition, as the result of a condition. And so, for example, let's say I was testing to see if this was a number, I was testing to see if it was greater than or equal to 8. Well, if it's greater than or equal to 8, it's going to have a 1 in one of these particular bit positions here on the left. Okay, shifting that to the right, or let's say I was checking to see if it was that exactly equal to 8. Well, if these right 4 bits is 8, okay, that's the binary representation of 8. By shifting this 3 positions to the right, I put that bit position all the way on the right all by itself, and now I can interpret the whole bit string as either true or false. In this case, since it's 1, it's true, and therefore I can use that result as a condition to run an if statement. Okay, so that's an example of a logical shift. Okay, now there's something else interesting about the shift, and that is if what we're shifting is an unsigned binary number, positive binary number, then shifting can also be used to implement multiplication or division. Okay, and let me show you what I mean for this one. Okay, so remember this value, okay, is in base 10 is 8. Okay, shifting 1 to the right, okay, basically lops off this 0 and puts another one over here. But if I interpret this value in binary, that's 4. And if I interpret this next value in binary, that's 2. And if I interpret this next value in binary, that's 1. So what I have done here as I have shifted one rightward each time is I've divided the previous value in half. 8 divided by 2 is 4, 4 divided by 2 is 2, 2 divided by 2 is 1. Okay? Now, what if I went the other way? What if I shifted leftward? Okay? If I shift this 1 position to the left, I wind up with this bit string, which is 0 in the 1s, 0 in the 2s, 0 in the 4s, 0 in the 8s, and a 1 in the 16 position. This value is 16, and in essence, what I have done by, by shifting this, trying to line this up correctly here. By shifting this value 1 position to the left, I have in essence multiplied it by 2. Okay. Remember, since this is binary, everything is in 2s. Okay. So the shift instruction basically can be used for 2 different things. One is it can be used to extract a single bit position and then interpret that as a logical value, true or false. Okay. Logical in the Boolean logic sense. But the other thing it can be used for is to do binary multiplication and division, where I'm either multiplying or dividing by 2 depending on whether my shift direction is left or right. Okay. So I've just showed using shift how to do multiply and divide. Okay. All right. Let's see. On to a few more. Then we have another one called branch. Okay. And once again, there's a few kinds of branch. Okay. Remember back in chapter 2, we talked about the difference between formulas and what did we talk about? We talked about the difference between formulas and between algorithms. And let's see if I can go find that example first. Okay, so here I've recovered the example that we went over in Chapter 2. This is an example of a tax schedule, okay? And we had a basic program here that we used to implement the tax schedule, okay? And in that basic program, both in the if statements and in some of the other statements, we had a lot of these go-tos, okay? So for example, here I input the income and then I test to see if the income is greater than $8,350. If it is, I skip over the instructions on lines 30 and 40 and go directly to the instruction on line 50 by executing this go-to statement. If, on the other hand, the income was less than or equal to $8,350, then I computed the tax using this formula, and then I did a go-to that jumped over all these other if statements and went straight to line 180, which is where we outputted the tax. Okay. Now, clearly the lines of this basic program are not CPU instructions. They're something a little more complicated than that. But the idea of the branch embedded in these go-tos is basically the same. Okay. So let's come back to this. Okay, so a branch, also called a jump, simply alters what instruction we're going to fetch and execute next. Okay, so this go-to, if executed, alters the instruction sequence. I'm not going to fall through to instruction 30. I'm going to jump over 30 and 40 and go directly to 50. Okay. This particular one on 40 jumps over 50 through 170 and goes through 80. This one on line 40 is an example of what we call an unconditional branch. If I get to line 40 and execute the branch statement there, I'm always going to jump to line 180. There's no question about it. If I get there, I'm going to do it. Okay. Whereas this go-to on line 20 is an example of what we call a conditional branch. Okay, there's a test I perform first to see if I'm going to execute that branch. If income is greater than 8,350, then I do the branch. Otherwise, I don't. That's an example of a conditional branch. Now, one way to think of this is to think of this as actually two separate instructions or two separate sets of instructions. Okay, one to evaluate the condition. In other words, one to say, is income greater than 8,350? Store that result, true or false, in a register. Then have the conditional branch instruction read the value of the register. If what's stored is true, then execute the branch. Okay. So the value was stored in a register as a result of a previous comparison instruction. In this case, the comparison instruction is income greater than 8,350. That's one instruction, CPU instruction. Result true or false gets stored in a register, and then we execute a conditional branch to line 50, which is based on that stored value from evaluating the previous condition. Okay? So, once again, two types of branches, unconditional and conditional. Think of unconditional as similar to line 40 here. Think of conditional as similar to line 20. Okay. All right, last one, pretty self-explanatory. Halt basically means you're done, stop, exit, you know. Okay. Now, actually in the bad old days being like back to the 40s or 50s or 60s, you literally had an instruction called halt, and when halt was executed, the CPU stopped. The computer just came to a grinding halt. Okay, and no more instructions were executed. If you wanted to start it up again, you had to load a program into whatever was used for memory at that time. Was it a stack of cards or a tape or a punch tape? And then you hit a button on the front that basically said start. Okay. In the modern world, you never halt the CPU, but you exit or stop the program that's running on the CPU, which typically transfers to some other program, usually the operating system. Okay. So, quickly reviewing the instructions we've gone over, we've got moves, which can be decomposed into various types: register to register, register memory address, or memory address to register. We've got the four basic Boolean logic operators, which could be, or operations, which could be applied in bitwise fashion or to entire bit strings. Okay. We've got add, okay, which does what you would expect, although there's typically multiple adds because we've got multiple types of data we could add together. We've got shift, which we can interpret two ways. One as extracting a bit that we'll use to test. Another is as arithmetic shift to do either multiplication by 2 or division by 2, depending on whether we're shifting left or right. Okay. We have Two types of branches, unconditional branch and conditional branch, and then we have a halt. Okay. Now, why that particular set? Okay, first off, let's count them up. We got one, well, let's count this as three. So we got three kinds of moves. We got four kinds of those. That's seven. What do we got? 8, 9. Maybe we count that twice, so it's 9, 10. We got two kinds of branches. That's 11, 12. And then we got halt. There's 13. Okay, and if we want to consider the Booleans to be different for bitwise and logic, there's 4 more, so there's 17. So depending on how you count, somewhere between a dozen and a dozen and a half instructions is what we've covered. Okay, why did I cover that specific set? Well, if you look back at the very earliest CPUs, what you will find is that set of instructions was what was in the earliest CPUs. And more importantly, that's all that was in the CPUs. Okay, so imagine a CPU that's only got 13 instructions. Okay, clearly that's not a very modern CPU because, for example, if we come back here and just start counting all the instructions in the Intel set, well, here's 30 or 40 different move instructions. Here's another 10 or so for binary arithmetic. Here's some more for decimal arithmetic. Here's the here's the bitwise logical operators. There's 4 more. What else we got here? Here's a set of another, I don't know, what's that, 30 of them. You get the idea. A modern CPU's got hundreds of instructions, okay? Whereas those earliest CPUs had just roughly this dozen to a dozen and a half we've covered here. Now you might say, well, a dozen and a half instructions doesn't sound like very much, So for example, let's take computation, okay? Well, you've got add, and well, you've just showed me I can do shift to do multiply by 2 or divide by 2, but is that enough to do all computation? Okay, what if I want to add something besides integers? What if I want to subtract? What if I want to multiply, but I want to multiply not by 2, but by 3, or 12, or 12.7629, okay? What if I want to, say, take a square root? Well, you'll have to take this on faith because I don't want to sit here and spend weeks discussing the intricacies of digital logic. But just take it on faith that given these primitive building blocks, given the add, given shift, okay, given halt or the halt and the Boolean logics, not and or, exclusive or, and the various forms of moves, you can use those primitive pieces to construct all the more complicated processing operations, such as subtraction, such as multiplication by things other than 2, so on and so forth. Okay. The bottom line is that set of roughly a dozen and a half instructions is enough to do everything that we would today consider to be what a CPU could do. Okay. Now, you say, well, if that's all we need, why the hell do I got 500 pages of this manual sitting here with what looks like hundreds of instructions? And of course, this is just the summary. I got to go to 2 other volumes to get all the detail. Okay. Well, just because I can do it using these primitive pieces here doesn't mean that's the most efficient way to do it. Okay. Why was this the way we did it, say in the 50s or the 60s? Well, think about the state of CPU design and fabrication in the 50s or 60s. Think about people sitting there wiring together vacuum tubes back in the 40s to make one of the earliest computers and its CPU. Clearly, putting together more than a couple hundred vacuum tubes was probably about all you could manage. Okay, well, if it takes 12 vacuum tubes to implement a move, and 3 to implement a not, and 6 to implement an and say 8 or 10 or 12 to implement an add, and so on and so forth, you've pretty much used up your vacuum tube budget by the time you've gotten to a dozen or a dozen and a half functions. Okay. So that's pretty much all you can stuff physically inside the computer. Okay, to do any more would generate so much heat that the whole thing would melt down, or would require so much electricity that you'd, have to build another Bonneville Dam right next to the room where the computer is, and it would take an extra 2 years just to sit there and solder all the wires together. And of course, by the time you started the thing running, one vacuum tube out of 100 burns out. Now you got to bring the whole thing to a halt while you figure out which vacuum tube you got to replace. So the bottom line is, the technology of the time simply wasn't up to building devices complicated enough to handle an instruction set this big. Because every one of these instructions has sitting behind it a whole bunch of electrical components. Nowadays, with modern, if it's Intel over there in Rio Rancho, we don't think twice about them shoving 1 billion transistors onto a single little piece of silicon. But back in the 40s and 50s, each of those transistors was not this, micron or 22 micron sized item. It was, it was a vacuum tube. I mean, vacuum tubes are big. They generate heat. They suck power. They take time to build. They take time to wire together. Okay, very different set of technology. Okay, so once again, the basic idea is that with this roughly 12.5 instructions, you can do everything. You just have to do a lot of work to do everything. Okay, so for example, in order to, raise x to the 1.5 power, you got to do a lot of adds, you got to do a lot of shifts, you got to do a lot of ands and ors and XORs. Okay, so this program you're reading from, where is that program? Let's see. Yeah. So this program you're reading from is pretty complicated. Okay, it has a lot of steps to do a fairly simple thing. Whereas in a modern processor, you can do that thing with relatively fewer steps because you've got a set of instructions that are custom designed to do some of those more complicated things, that have essentially, pre-wired extra sets of transistors together to do some of these complicated steps. Okay, and we don't necessarily think of them as complicated. I mean, for example, subtraction, is certainly, so subtraction, multiplication, division of unsigned inside, incrementing, decrementing, negating, comparing. We wouldn't have had these instructions in that earliest CPU, but we could have executed sequences of ORs and XORs and ANDs and adds and nots and shifts to do the same thing. We just would have had to execute, several, a handful or several dozen of these to do what in a modern processor I can do by executing one instruction. Okay. What I'm getting at here is the difference between simple and complex instructions. Okay. And I've got a fairly simple example here that I want to walk through and to show you how we can, using just the primitive building blocks we've already covered, do something a little more complicated, and that something is subtraction.